Hello, in this video, we'll tackle one of the foundational models of computability and theoretical computer science named Turing machines. These machines are named after the famous mathematician and computer scientist Alan Turing, known by his valuable contributions to advance the computer science domain. Especially, he's very famous with the techniques he devised for speeding the breaking of German ciphers during World War II. Also, you might have heard his name when you started artificial intelligence because he addressed the problem of AI and proposed an experiment well known as the Turing test. Before diving deeper into the concept of Turing machine, let's recall what we have already seen so far. Recall that the smallest set of languages is the set of regular languages. A regular language is a language that is recognized by a finite automaton. A finite automaton may be deterministic or non-deterministic. We have seen that these machines have a very limited memory. For example, we can recognize the set of strings composed of a list of A's followed by a list of B's, but we cannot count the number of one of these symbols. Instead, context-free languages are a wider set of languages which contain already the regular languages plus extra languages which they can be recognized by push-down automata. A push-down automaton is a machine that is similar to non-deterministic finite automaton, but it can use a stack as an auxiliary memory. For example, here via this stack, we can count the number of A's that precede the set of B's, and then we can use this number to recognize the exact number for the symbols B. Let's recall the schematic diagram behind the push-down automaton. This machine will have a possibility to push and pop elements from a stack. For example, for the strings a to the n, b to the n, the machine will take an input, say for example triple A followed by triple B. It will read the input. Whenever it finds A, it will push A in the stack. For the second A, it will push A. For the third A, it will push A until reading the part of the B's. Now, with each B read, we'll pop A from the stack. In this case, it's possible to recognize strings with the same number of A's and B's. At the end, we will accept the string if the stack is empty. If there is remaining symbols on the stack or remaining symbols here in the input, the push-down automaton will not accept the string. This is powerful enough for this context, but for example, if you want to read A to the n, B to the n, C to the n, with the third part containing C's, we can use the stack to save the number of the elements A. For example, here with each A read, we will push A on the stack. Then with each B, we will pop A from the stack. In this case, we have guaranteed that we have the same number of B's and A's, but when we will reach the third part of C's, we don't have any information about the number of A's or the number of B's. We can't use the stack. The stack is empty at this moment. So there's no remaining information in the stack to help in counting the number of C's. This is one of many examples that can be used to show that push-down automata are recognizers for context-free languages like this one, the set of strings A to the n, B to the n. However, they are not powerful enough to recognize context-sensitive languages like A to the n, B to the n, C to the n, or more general languages. In fact, the stack is a very powerful tool that can be used when we need a memory accessible via the last in, first out technique. But in the general case, we need a more powerful device in order to ensure more flexibility and more generalizability to access to the given memory. We'll show next that this is possible via the use of Turing machines. Proposed by Alan Turing in 1936, these machines consist of abstract computational models that performs computations by reading and writing to an infinite tape. They are capable of simulating common computers. In fact, if we have enough memory, any problem that a computer can solve will be solvable using a Turing machine, and vice versa. So the tape here will represent the memory. It's an infinite set of cells in which we will write the given input string to be recognized by the Turing machine in the first cells of the tape. Here, for example, if the input is double A, double B, double C, we will write this input in the left cells of the tape. The remaining cells will be blank. So it's supposed here that if we will find this blank symbol here in this cell, it means all the cells to the right are empty. There is no symbols of the alphabet there. These cells are there to be used if we need them. With the tape, there is a head here. It's like a pointer on a specific cell. At each moment of the computation, this head will point on a cell. This head can be used to read what's there in that cell. Also, it may be used to write a symbol on the cell. For each transition of the machine, the head will move one cell to the right or one cell to the left. So this is the basic idea of a Turing machine. We have a state transition diagram here that will define in each transition what is the symbol to read on the tape, what is the symbol to write in this current position, and what is the move for this tape head, if it's one cell to the left or one cell to the right. So in other terms, we have a machine that will monitor what will happen in the tape given a specific input. For example, here let's take the language A to the N, B to the N, C to the N, and let's take a specific input here which is double A, double B, double C. So this input will be written on the tape, and then according to the state transition diagram, we will allow for the following instructions. At the beginning, we will say that we will read the A and we will cross it out. It's like we will say that we have visited this A. We already have seen this A. Then we will go right looking for a B. We will go to the right one cell, then another cell, until finding or reading a B. In this case, we will cross it out. We will cross out this B to mention that we have already read this symbol. Then we will keep going right until finding a C. The first time we will see a C, we will cross it out. Now we have crossed out one A, one B, one C. In this way, we know that for this A, there is a corresponding B and a corresponding C. Now for the rest of the symbols, we will keep going left until reading a symbol A. Then if we came to this cell containing the A, we will repeat the steps from number 1. So we'll cross out this A, keep going right until finding a B that is not crossed out, and we will cross it out. Then keep going right until finding a C that is not visited, and we will cross it out to tell that we have already visited this C. Now we will accept if all the symbols on the tape are crossed out. If it happens that all the symbols are crossed out and we are reading now a blank here, an empty cell, in this case only we will accept the string. So in short, at any moment we saw that the machine we'll have the possibility to read the current position via the head, the tape head. It will have the possibility to write on the current position. For example, write a cross T here or another symbol named X, Y. We can write on the current position. Also, we can move the head of the tape just one cell to the left or one cell to the right. To make these operations possible, we will write them on the transition. This will result in showing on the transition what is the symbol to read on the tape. And then we have also to show what is the symbol to write in that place if we take this transition. And we will define what is the move on the tape. If it's left, we will write L, and if it's right, we will write R. This way is defined the transition function delta. So to define this transition, we need to know what is the state from which we will make this transition and what is the symbol that is pointed by the tape head. In other words, what is the current symbol on the tape. And this will result in three information: the next state, which is P, the symbol to write on that cell, and the move that will be done on the tape. So formally, a Turing machine is defined by a tuple of 7 elements: Q, sigma, gamma, delta, Q0, Q accept, and Q reject. Q and sigma are the set of states and the set of input alphabet, just like for finite state machines. Gamma is the tape alphabet. It will contain all the symbols that will be written on the tape. Note here that sigma is included in gamma, so all the symbols of the alphabet will be part of the symbols of the tape. Also, we'll have the blank symbol that is included in the symbols of the tape. The blank symbol couldn't be part of the input alphabet because if it's the case, we will not be able to differentiate between the symbol that is part of the alphabet and the blank symbol that is used to denote the end of symbols of the tape. And then we have the transition function delta. The input for this transition is a state, a member from Q, and a symbol of the tape, the symbol that should be read from the tape. The output to this will be a state, a symbol to write on the tape, and the move if it's right or left. Then we will have a special state which will be the initial state. It's denoted Q0. We will have another special state which is Q accept. It's an accepting state. This means that when the machine reaches this state, it will halt and accept the input. Q reject here is another special state, which is a reject state, which means that when the machine reaches this state, it will halt and reject the input. Reaching Q accept or Q reject means that the machine will halt directly. It's not like for the push down automaton when we have to accept only if the stack is empty. Here it's not the case. Here when the machine reaches one of these states, it will halt directly by accepting or rejecting the input. This is too useful for the definition of the transition function. In fact, here the transition function is a total function. It should be defined on all the inputs. So here we say that for a Turing machine, the transition function is a total function. It's not partial. It's defined for all its domain.